Okay, hello everyone, and welcome to another IRENE online seminar. So before we start, let me tell you a couple of things. First, this talk has been recorded, and I think Anna will have the video available early next week, so you can share it with your friends and family if they're interested in nuclear astrophysics. That will be on the JINA YouTube page. So if you have questions during the talk, as always, we'll have a discussion session at the end of the seminar. And also we'll also have an informal session with our speaker later after the seminar at GatherTown, and I will post the link for the room after the talk starts. Okay, so it's my great pleasure to introduce today's speaker, Dr. Annika Lennarz from TRIUMF. This is a short bio. Annika finished her PhD in 2015 at the University of Minster. However, she did her thesis work with the Titan group at TRIUMF. Then she moved to the Dragon group, also at TRIUMF, as a postdoc, where she led many experimental efforts of the group that she will talk to us about today. Since 2020, she's a research scientist at TRIUMF, and since last year, she's also an adjunct professor at McMaster University. Dr. Lennartz's research interests include all kinds of aspects of nuclear astrophysics, especially nuclear reactions and measurement of nuclear masses. And a small information that you might not be so interested, but I want to say, is that she was also an important link for a collaboration with the TRIUMF and a brewery in Vancouver a few years ago, where they brewed a beer called Star Stuff, an India session ale. So today, Annika will talk to us about nuclear astrophysics with a Dragon recoil separator. So Annika, the stage is yours.
Thank you, Thanasis, for the very nice introduction. It reminds me of good times. So yeah, let's talk about star stuff. Let's talk about nuclear astrophysics with the Dragon recoil separator today. And first of all, first of all, let's begin with a little introduction as to why we're interested in these type of reactions in the first place. So the investigation of astrophysical phenomena has been one of the key aspects in nuclear astrophysics research for a long time. And astronomical events like supernovae, novae, and exobursts, they all leave imprints in our observable universe in the form of the chemical elements. These signatures are detectable via satellite missions, for example, or modern terrestrial telescopes. And the optical spectra, they leave signatures in the UV and the infrared, for example, and that gives us information about the elemental abundance distribution. So there's really what we need to understand is the nature and the role of the nuclear reactions that govern the energy release and the nucleosynthesis path in these explosive scenarios. So there's essentially three main drivers that push the frontiers and that define the challenges. And we have the famous multi-messenger observations, we have the computational models, and we have the tool of nuclear experiments and nuclear theory feeding information for the computational models. Now, we want to answer the questions. What are the origins of the various groups of isotopes in the nuclear landscape? And what are the roles of nuclear reactions in the stellar evolution? So let's start by just having another look at the nuclear landscape. I'm sure like most of you are familiar with this. Nevertheless, anyone who hasn't seen this, I'll just reiterate quickly. This is our way of classifying isotopes by means of the neutron and proton number. So we have the proton number on the y-axis and the neutron number on the x-axis. And as you can see here along the diagonal in black, you see the path of stable elements. And the arrows over here, they indicate all types of different nucleosynthesis reaction pathways, starting from stellar fusion all the way up to iron along the RP process that's thought to be responsible for the synthesis of elements all the way up to the tin-tellurium region. The MAP process thought to occur in, for example, the proton-rich ejecta in Recoils supernovae, and then following along the path of the stable isotopes, we have the slow neutron capture process, which is a series of slow neutron captures followed by much faster beta decays, thought to be responsible for the synthesis of elements beyond germanium. And the other half of that, of those elements is thought to be synthesized by the R process, the rapid proton, so the rapid neutron process, which is relatively famous. However, the site of this process is not known unambiguously at this point. So in all of these stellar fusion and explosive nucleosynthesis passes, there's an important class of reaction called radiative capture reactions. So you have proton alpha induced reactions, and it's essentially a two-body fusion reaction where you have a bound state of a fine nucleus that is reached via gamma emission. And there's really hardly any astrophysical burning or explosive scenario where these reactions play no role. So when I talk about radiative capture, what exactly do I mean? So we have essentially any reaction where a bound state of the final nucleus is reached via the emission of electromagnetic radiation. And this can happen via two competing mechanisms, essentially. There's the case of direct capture. It's a one-step process where you have the projectile that makes a direct transition from the continuum into a bound state. So you have a photon emission without the formation of an intermediate state. And this process is somewhat comparable, if you will, with like the Bremsstrahlung or capture, continuum capture, where you have many closely spaced levels that are contributing. And the other case is where you have a resonant case. It's a two-step process. And here it's indicated on your right, where you essentially have the formation of a compact nucleus, a virtual state, prior to the emission of the photon. And unlike the direct process, the contribution of the individual excited states in the resonant case, they give rise to these large enhancements in your capture cross-section. And so you have a large energy dependence associated with it. Now, why are they so important for nuclear astrophysics? So that's because they're kind of involved in all of these burning scenarios and explosive scenarios, so from the PP chains all the way up to nucleosynthesis and novae, X-ray bursts and supernovae. And for many nuclei, the proton alpha-induced reactions, these are the radiative capture ones, are the only ones with a positive Q value available. So the knowledge about these reactions is essential to understand the reaction pathways. Additionally, they proceed relatively slowly compared to strong interaction and are thus rate-limiting steps. So they really control the pathway and the reaction cycles. Now, this is the problem is that they're difficult to measure because the cross-sections are vanishingly small. And that's kind of indicated in this cutout of the nuclear landscape on the left here, where you can see there's been a lot of measurements along this value of stability, so involving stable isotopes, so capture on stable isotopes. However, as soon as you move away from this, you're getting into into more trouble, and it's more difficult to measure these capture on radioactive isotopes. Now, what do you do? What's the solution to overcome these issues? First of all, the vanishingly small cross-sections. So you need intense beams to study this in low background environments. At the same time, you need to find a way to overcome the issue of overcome the challenges when it comes to measurements of radioactive capture on radioactive nuclei. Now, the solution in this case would be inverse kinematics as keyword. That's necessary because it's infeasible to make targets of short-lived radioactive isotopes, essentially not just infeasible, in many cases impossible. So you're coming in instead with the radioactive isotope beam on your stagnant target. And the other advantage here is, as indicated on the bottom, that if you have the, in terms of recoil detection, the gamma ray carries relatively little momentum relative to the recoil. So you're having a forward-focused cone, which helps you later in terms of actually being able to separate it in your recoil separator from the beam. But details about this later. Now, let's have a look at the inverse kinematics sketch that I have here on the left. So we're looking at recoils from inverse kinematics reactions. So we need to understand the momentum spread and the recoil cone angle. And essentially you have the scenario where you have a beam particle with mass m1 and laboratory energy T1 incident on target particle with mass m2. Together, they form a so-called compound nucleus, which has a mass m3 and plus some excitation energy. And then from energy conservation, it follows that the energy of this compound nucleus is essentially the laboratory energy of the incoming beam minus the center of mass energy of beam and target. In the next step, when you have the de-excitation and thus the emission of a gamma ray, this removes energy from your system. And so you end up with always lower energy of your recoil versus the beam particle. Now, so in the following, I'll talk about the advantages and details of operating gas target and detecting the signatures associated with the radiative capture decay. Now, first of all, the first step is finding a place to do these measurements. And this is where TRIUMF comes into play. TRIUMF is Canada's Particle Accelerator Center, located in Vancouver. And here we're making use of radioactive isotope beams that are produced at TRIUMF by means of the ISO method, meaning we're having a proton driver beam that is created in the cyclotron, which is actually with 18-meter diameter, the largest cyclotron in the world. And you essentially accelerating H- in a sector focused cyclotron by means of a 23 megahertz alternating electrical field. And then upon extraction, these H- pass the carbon foil and stripping off the remaining electrons. So you're left with a bare proton beam. This proton beam is then, as you can see here in the sketch, coming from the cyclotron, sent to our target stations, which are thick production targets. And this is where the isotope separator and accelerator facility comes into play, which provides a large variety of intense beams of rare isotopes that are then further accelerated to the desired energies to various experiments, including DRAGON. Now, DRAGON receives energies of the order of 150 kV per U to 1.8 MeV per U, which is actually a suitable energy regime for reaction studies, for example, on reactions relevant for novae or X-ray bursts. Now, let's talk about details on DRAGON. What exactly are we measuring? So laboratory measurements for nuclear reaction cross-sections, we're first of all measuring a reaction yield, meaning the reactions occurring over the number of beam particles incident on the target. And in this case, then it's the number of recoils that we're detecting in our end detector over the number of incoming beam particles folded in with the detection and transmission efficiency. And the total yield is related again to the cross-section integrated over the target length via this relation where you have the cross-section, the number density, and the effective length. Now, for narrow resonances, the thick target yield, so when I'm talking about narrow resonances, I mean the width is narrow, very narrow compared to the width of the target, and it's related to the resonance strength via the following relation. So you see the dependency of the strength on the yield, the radiative wavelength, the stopping power, which is the energy loss per target atom per unit area, and the target and projectile masses. Now, keeping this formula in mind, let's move on to details on the separator itself. So here we are, DRAGON, standing for Detector of Recoils and Gammas of Nuclear Reactions, essentially consists out of 4 different parts, if you will. So we have the windowless gas target, which at the very beginning of DRAGON, we have incoming beam on the gas target, creating the reaction that's indicated in here. So it's filled with either helium or hydrogen, depending on what type of reaction we're studying. And then that's surrounded by a BGO detector array for detecting the gamma rays that are following the excitation of the compound nucleus. Now, after this, we have the main part of DRAGON, which is the 2-stage separator consisting of 2 stages of separation, each consisting of a charge selection via magnetic dipole and mass selection via an electrical dipole. And in the end, recoils are transmitted to our end detector, indicated over here. Now, again, measuring the yield results in the resonance strength if you have all involved parameters available, and then this feeds into the thermonuclear reaction rate linearly, and the resonance energy feeds in via the exponential term. And we also have means of determining the resonance energy under certain conditions, which is something I'll also mention in a bit. This is a picture of DRAGON. So you can see the electrical dipole here, a magnetic dipole here, the other electrical dipole here, and the end detector station indicated in this area. The windowless target is on the other side, but you can't see it on this picture, but I have another one for you. It's well hidden. So, so the DRAGON gas target is a windowless, differentially pumped, recirculating gas target, as I said, either helium or hydrogen, depending on what we're studying. It can hold pressures up to around 8 torr without, before we're running into pumping constraints. We're usually operating at around 5 torr in the target. So you see this trapezoidal shape here, which is kind of chosen to help deflecting the gas back into a recirculating system, indicating via this gas inlet. And the recirculation happens via a series of 5 Roots blower pumps through an LN2 cooled zeolite trap for cooling and cleaning the gas, and then going back into the gas cell. So this is a contained signal, system as soon as we're running. Now, while we are maintaining pressures around 5 torr in the center of the target, we want to have low pressures just upstream and downstream of this. And that's achieved by a series of Roots turbo pumps along the pumping tubes. And so we are able to reach like 6 orders of magnitude difference in pressure just after the target, which is essential because otherwise you would run into issues with charge changing collisions when the recoils emerge from the target. And just one other thing that I didn't mention, we have 2 surface barrier detectors in here that detect elastically scattered particles for normalization purposes. Okay, and this is now a picture of the target that you weren't able to see before, where we have the target in the center surrounded by the BGO detectors, and we have turbo pumps on either side to aid the differential pumping. Okay, a few more details on the target. So again, going back to this formula, we require knowledge of the stopping power. So again, the energy loss per target atom per unit area. And the issue is in predicting the stopping power with semi-empirical models that there's usually still high uncertainties associated with this. So it's always recommended to perform a direct measurement of the stopping power, if at all possible. And this is usually what we're doing by relating the energy loss to the incoming and outgoing energies. This, however, requires also knowledge of the effective length of the target. It's indicated here. And to measure this, this has been done as an example with well-known resonances. So you're basically doing a scan of your beam energy where you know exactly where the resonance energy is. And you can see when the beam comes on resonance, so it lost enough energy in the target to go on resonance, you have an increase in your gamma yield, and then it drops off again as soon as you're off resonance with the beam. And the effective length is essentially defined as the distance between the 2 points where this gamma yield has fallen to half of its peak value. Okay, so understanding this, we now have to deal with detecting the signatures of our radiative capture reaction. So one signature is, of course, the gamma emission, and we're using a BGO detector array in our standard configuration to detect these gamma rays. And we have efficiencies of the order of 40 to 80%, very much depending on the type of reaction and the energy. And combining this coincidence signal will help us later to really suppress the background in our particle identification. issue is that we depend on JINA simulations for our detection efficiency, and this is actually something that dominates our systematic uncertainty for the experiment. And the other disadvantage is, of course, that we have limited energy resolution with the BGO detectors. However, the advantage is the high efficiency and the fact that we have a segmented array. And that means we have some position sensitivity. So this is a simulation demonstrating this. So you have the counts as a function of the Z coordinate in the BGO array, in the Z coordinate of your target. And you can see if it's nicely centered in the target, then you have this type of distribution. However, if you're coming in, for example, with like too low energy and the beam goes on resonance too quickly, then you're going to see this type of distribution where you have a resonance occurring slightly upstream of your target center. Now, this, of course, if you have enough statistics, helps you to slightly adjust the beam energy or the gas pressure to put your resonance in center of the target. But it also gives you a way of determining the resonance energy, because you can relate the centroid of this distribution to your incoming and outcoming beam energies. However, this is a method that's only possible with high statistics, and we are in the process of finding a better technique. Now, let's move on from the target. We created the reaction. Now we have to enter the separator. And here the geometric acceptance is important as it defines the type of reactions that we can actually measure. This becomes important in one of the experiments that I'll be introducing later on. And we have to understand what is the maximum possible recoil angle. And that's the case when we have the gamma energy maximized, which is the case when it equals the Q value plus the center of mass energy of beam and target, and if the emission occurs perpendicular to the incident beam direction. And the recoil cone angle can be approximated by this relation, which has a minimum when the center of mass energy equals the Q value. And nominally, Dragon has an acceptance of plus minus 21 millirads. Now, keep in mind now the minimum. So the local behavior of this function is essentially important for us to decide which type of reaction can we study and at what type of energy can we study this reaction. You can see here the maximum recoil half angle as a function of the center of mass energy, picking the reaction with the lowest Q value in this example is beryllium 7 P gamma. And you can see that you have an increase in the cone angle as a function of center of mass energy because of the low Q value. And the opposite case here is 23 sodium P gamma with a Q value of 11 MeV. So you have an overall decrease in the angle versus center of mass energy. So that's an important consideration when you're performing your measurements or you're planning for the measurements. Now I want you to keep in mind, though, that this is only the case when you have the entire center of mass energy converted by the transition of a single gamma ray into the ground state. Then you have that scenario. However, in reality, it's mostly, in most cases, you end up with some type of cascade decay, and that's indicated over here. So you end up, when all of these decays go in some direction into your center of mass system, you end up with a polar angle, and that's indicated here. Polar angle versus the maximum recoil angle in the 100% ground state case versus the cascade case. So you can see that actually most of your recoils would be within the acceptance limit. And the broadening of the function, we also have beam divergence and some straggling in the target that's to be considered. Now we know which recoils made it out of the target and are within our acceptance. And now the issue is that because of beam target and recoil target interactions, the beam and recoils, they will emerge in a distribution of charge states and a range of charge states out of the target. And the most populated one is usually of the order of 35 to 50%. So we need to find a way to only extract the most populated one. And of course, here we're using the magnetic dipole, which is indicated over here, to then separate the different charge states by means of forcing them on different bending radii with the magnetic dipole. And so we have a distribution, a spatial separation in our focal plane. And then we're just using a set of slits to basically suppress any of the unwanted charge states, and only the particles with the right magnetic rigidity can actually make it all the way through the separator. And then following this, we have the second stage of separation, where we have mass selection by means of the electrical dipole. And here we can just use the fact that beam and recoil are emerging at roughly the same momentum. However, they have different mass, which means they have different kinetic energy. Sorry, they have different velocity and different kinetic energy. And that's what we're using to separate them. That's by sending them through these concentric electrodes, and only the particles with the right electric rigidity can actually make it through this separating device. And ultimately, the capabilities of our magnetic and electrical dipoles define our rigidity of the Dragon system. Now, finally, we made it all the way to the focal plane, our detector system, which consists of, first of all, MCP-based timing detector. And that means we have two diamond-like carbon foils, which are actually in the beam path. And when the beam or recoil passes through, you have the creation of secondary electrons, which are then deflected into the MCPs, creating our signal. And we have two of them, so we are able to have a local time of flight system, local time of flight signal in place. And this is just a picture of what this actually looks like when you're taking out the MCP system. So with the mirror over here, MCP on the foil on the other side, and MCP sitting over there. Afterwards, the beam can either be detected, or the recoils can either be detected in a DSD silicon strip detector for good energy and position resolution and timing resolution, or in an isobutane filled ionization chamber, which is used for Z identification. Now, just a few examples on what this actually looks like. This comes in, this extra separation capability and identification capability comes in handy when you're dealing with beams that are not just containing the species of interest. So when you have isobaric components, for example, as an example, we have the neon 19 and fluorine 19 beam cocktail, where the species of interest was actually neon 19, but it came along with a lot of fluorine. And your ionization chamber is a good way of separating between them. And it also gives you separation between possible recoil products produced by capture on the unwanted beam component. So in the end, worst case, you could even end up here with 4 different species in your ionization chamber. But as long as you're able to separate them, everything is good. And just a few more examples on the power of the separation capabilities with the time of flight. Here we have the local time of flight between the MCPs and the separated time of flight, which is the time of flight ranging from the detection of the gamma ray in the at the gas target all the way to the detection in the focal plane. And you can see a nice cluster of events, which is with hardly any background events. And similar trick here, just with the IC as an additional gate. And we also have a hybrid version, actually, where we have a DSSD operated in isobutane. And here you can also achieve nice separation in singles when you have this detector installed. So you don't even need the coincidence signature indicated here in red to have a clean recoil signal. There's a lot more tricks you can play in the end with an advanced analysis to suppress your background. Now, all of these, like the intrinsic separation plus your particle identification, leads to high suppression factors for the Dragon recoil separator. And the example here is for proton capture, where you have increased suppression factor as a function of beam energy, which is largely due to the divergence of the beam at lower energies. So you're running into issues with aperture scattering and more scattering in your separator, leading to higher background in your end detector. Whereas for higher energies, you don't have that issue anymore, and to such a degree. And then we have even a larger suppression capabilities for the alpha gamma reactions. And then combined with the coincidence measurements, we're reaching up to around 10 to the 15 for proton capture or 10 to the 17 for alpha capture. So it's really not just one value, but it really depends on a lot of different factors. Now that we understand how DRAGON works, let's talk about a few recent experiments that were performed at DRAGON. So this one is a study that we actually just published in PRL. So it's very exciting because it was the first direct measurement of radiative capture on an isomer using isomeric beam that was produced at TRIUMF. Now, why are we interested in this reaction in the first place is because Aluminium-26 is an interesting case. It's a radioisotope on the one hand. So it provides insight into the nature of nuclear processes in our stars and our galaxy. And its existence has basically been proven by observing isotopic excesses of magnesium-26 in meteorites. So this gives hints to nucleosynthesis in the early solar system. And we have the observation of the characteristic 1.809 MeV gamma ray, which hints to active nucleosynthesis in our galaxy because of the relatively short half-life on the cosmological scale. However, the issue is that the actual origin of it has not really been finally resolved. There are some suggestions from studies on presolar grains that suggest it could be nova or AGB star origin, or satellite missions that hint to massive stars and quark-collapse supernovae. But in reality, it's likely all of the above, but we need to understand to what extent which astronomical site is responsible. The problem, however, is that the nucleosynthesis of aluminium-26 is complicated by the existence of an isomer, which sits at 228 keV above the ground state, as it's indicated here. So this isomer undergoes a super loud beta plus decay, 100% to the magnesium ground state. What this means is that it's bypassing the emission of the 1.809 gamma ray. So this is kind of disturbing our ways of our signature of aluminium-26 in this way. So it influences the abundance of magnesium-26 in ejecta of explosive astronomical events. It plays a critical role in understanding the origin and the content of aluminium-26 in presolar grains. And so it really affects all three observational signatures that are listed here of aluminium-26. So we need to find a way to reduce the uncertainties in the reactions that are responsible for producing and destroying the isomer in stellar scenarios. There's been a lot of effort and work going into studying, first of all, the capture on the ground state. However, very little information was available until recently on the isomeric reaction. The issue here is that it's difficult to produce pure isomeric aluminium-26 beams to probe the low-lying excited states in silicon-27. There have been indirect approaches to study this reaction, and the first one, there's one from Deibel and others in 2009, which did an indirect approach via aluminium-27 through helium-T, strata exchange, and then observing the proton decays from the excited states that were found. And one was found at 445 keV. So it was already very interesting. However, this energy was also very close to the cutoff energy threshold of that experiment. So there was another study shortly after from Lothar and others that identified low-lying states in the isomer plus proton system. And they confirmed the existence of this resonance as slightly adjusted energy and also made a spin assignment. And they also found 4 other energies. resonances, however, with unknown strength at this point. So the case continues. There has been a recent study by Helium and others that used, based on isospin symmetry, they mimicked the proton capture on the isomer by doing a transfer reaction on silicon-26. And from that study, they concluded that there are no strong single particle states were observed, and they could put like stringent upper limits on the spectroscopic factors for all the resonant levels that they were able to see under 500 keV, the center of mass system. Among them, for the 447. And the interesting thing here was that they estimated a relatively high strength for this resonance, which then meant that it was likely to dominate the entire isomeric rate for temperatures above 0.3 gigakelvin. Now, of course, we wanted to perform a direct measurement of this, and that has been done at Dragon using a beam consisting out of ground state component and isomeric component. And first of all, we were making sure that we had our systematics and the separator under control by measuring a reference resonance in the ground state system at 369 kV, putting that into the target. And you can see the beautiful, nice background-free cluster of events when you're looking at the separate time of flight system, separate time of flight versus your local time of flight. And these events appear again in the ionization chamber that was used for this experiment. And they're all clustered here, so far away from the unsuppressed leaky beam, as we call it. Now, once this was done, we tuned the separator and the beam energy accordingly to put the isomeric resonance at 447 into the target. And again, after a couple of days of measurement, you could see this nice, beautiful cluster of events coming up, and really literally free of background in this case. And all of these events also have an ionization chamber event, which is indicated over here. And again, you have separation between leaky beam and recoils. So this was very exciting. And of course, we try to assign a resonance strength from this yield, and that has just been published. And the result is that, first of all, for the reference resonance, we're in beautiful agreement with literature, even able to perform a singles measurement, not even using the coincidence signature because we had good separation. And the strength for the 447 turned out to be high. So we measured 432 milliatom volts, of course, with a large uncertainty. Now, interestingly, this was consistent with the estimates given by the recent study by Helen and Lothar and others. So with this result for the omega gamma in the isomeric rate, it suggests that the 447 would govern the entire isomeric rate in the peak temperatures where that's relevant for classical novae or supernovae. And just as an example here, you have the thermonuclear reaction rate and the contribution of the individual resonances to this rate, and you can see the 447 in red dominating this. We also compared this to previous reaction rate compilations. You can see, for example, that for the reactive, we're at least a factor of 5 higher in the supernova temperature range. However, in the overall range, like previous procedures of adopting just the ground state rate because of the high uncertainty in the isomeric one beforehand were not too far off in the first place. However, now the next interesting step is, of course, to measure the other resonance that have been found and where only estimates and predictions for the resonance strength exist. So anything above this energy. And there's also an energy at 218 for which we have to find an indirect way of measuring it. Now, this was a very exciting experiment. And let me just show you another example where we used radioactive ion beams at TRIUMF, which is beryllium-7 alpha gamma, which was Lennarz's experiment proposed by McMaster at McMaster University. And we worked on this measurement campaign for a couple of years. And it's an interesting reaction because it's a breakout reaction from the PP chain to the CNO cycle. and it affects the proton to seed ratio in the early MEP process in core collapse supernovae. And as such, it influences the production of the P nuclei in the mass range between 90 and 110. So if you have a look here at the nuclear flow versus the temperature, you can see that in this temperature region where the MEP process is occurring, you have a competition between the triple alpha process and the rhodium 7 alpha gamma, and some other reactions are involved as well. Now, the issue is here, you need to understand really the individual contributions of these rates, because they influence the production of seed nuclei. And if you have more intermediate mass nuclei, then they act as proton poison, and then the MEP process becomes less efficient. So it's like a very complicated entanglement of reactions that will influence the production of elements in these stellar scenarios. It's also thought to be important in low metallicity stars. However, despite its importance, there's hardly been any direct studies on this reaction rate. Now, the goal was to reduce the reaction rate uncertainties at MEP process temperatures between 1.5 and 3 gigakelvin. And for this, previously unknown resonance strength have been measured. So you might think, okay, why hasn't this been done before? So first of all, TRIUMF is a place where you get the beryllium 7 beams available that you need to do this measurement. And the other issue was that for DRAGON, if you remember, we talked in detail about geometric acceptance. This reaction exceeds, the recoil cone exceeds DRAGON's acceptance by a factor of 2. So now it becomes important to understand really your simulations and your systematics that are involved in transmitting the recoils through your separator. Now, we could say, okay, it's too difficult, it doesn't work, we give up, or we could just try and benchmark our separator, and that's what has been done by studying a well-known reaction and well-known resonance in a reaction that has similarly large cone angle, which was lithium 6 alpha gamma. And that's what you see here. So you have a nice clean signal of the recoils in our separate time of flight system signal. And we were able to reproduce the literature resonance strength quite well within the uncertainty. So this gives us confidence that DRAGON is capable of handling measurements, even when the maximum recoil cone angle exceeds the acceptance. So we really understand these simulations really well. Now, to the actual science case. So we have here the, again, separate time of flight signal, just to demonstrate the cluster of events for one of the resonances that we measured. We measured 3 in total, 1 known one, or like at least the strength has been measured before, and 2 unknown strengths. And this work has now been submitted to PRL and PRC recently. So to sum up here, as a result, it performed measurement of 2 unknown strengths, and in total was able to reduce the uncertainty in the reaction rate quite significantly in the relevant temperature window for the neutrino P process compared to the previous NACRA rate, which was around 78 to 86%. And that's indicated here. You have the new thermonuclear reaction rate, and down here you have the relative rate compared to the previous compilation. You see still the largest difference is below 0.3 gigakelvin. However, this temperature range is not relevant for the MEP process. And you can see a slightly smaller, slightly reduced rate in the irrelevant temperature range, which may lead to the conclusion that you have a more efficient MEP process because there is an increase of free neutrons that are available relative to the seed nuclei. Now, the other thing is, it's not just the science case is interesting, but also the experimental part of this means that there's a whole new range of reactions that may become accessible with DRAGON that previously were thought not to be measurable due to the limitations on the cone angle. Now, these were just 2 examples of recent highlight experiments. And now I'm just going to give you a quick preview on what's coming up at DRAGON. So we're going to trying to make DRAGON more versatile and One option has already been used at DRAGON is to completely remove the DRAGON gas target and replace it with SONIC, which is our scattering chamber of nuclear and inverse kinematics, which is also a windowless extended gas target, however, surrounded by 30 ion-implanted silicon charged particle detectors that are mounted on telescopes at precisely defined angles. And that allows for measuring scattering cross-sections at 3 different angles at one given beam energy. So it has already been successfully commissioned already a few years ago, and the next experiments coming up would be beryllium-7 alpha-alpha and beryllium-7 pp. So hopefully this will happen in the near future. And then something that will happen, this is just another picture of SONIC when it's installed. And now something that will happen this spring is actually a merger of the Griffin high-purity germanium clover detectors with our DRAGON gas target. And that has been done to, as a consequence of a proposal suggesting to remeasure states in the neon 20p gamma reaction, which is part of the neon sodium cycle. I think it's actually the slowest one this cycle. So it really determines the reaction flow, reaction pathway in this cycle. Now, the issue here is we needed the detectors to increase the energy resolution. So really to disentangle the individual contributions from the state of interest, which would have not been possible with the current BGO energy resolution. This will be happening very beginning of the schedule, so either end of May or early June this year. And all the preparations are presently ongoing. And here is just a picture of one half of the frames of the holding 3 of the total of 6 detectors. Now, I'm probably just going to skip over this in the next plans because I already talked about this slightly. And just summing up, I would say it's important to remember that DRAGON is still one of state-of-the-art experiment. So it's really holding still the record for measurements of radiative capture actions on radioactive isotopes worldwide. And we're in the middle of upgrading our capabilities by experimenting with lanthanum bromide array, as you saw the HP germanium clover detectors, and there's also plans for a possible neutron detector array. So you're really having ultimately a variety of setups that you can apply to measure different types of reaction properties. And yeah, with this, I would just like to thank my collaborators and thank you very much for your attention.
Thanks a lot, Annika.
Yeah.
Okay, questions? You can raise your hand or you can unmute and talk. Okay, people are shy, so I might start.
Crystal clear. Okay,
Yeah,
there's one hand.
Oh, there's one hand. Yeah, Nabin, go ahead.
Hi, Annika. Nice
Hello.
talk.
Thank you.
So I had a question regarding uncertainty. So what is the uncertainty that you expect in a let's say in a typical experiment regarding the charge state distribution or the efficiency in total?
Yeah, so in total, so if you, I think I mentioned this at least for the coincidence analysis, that the main part of the systematic uncertainties results from our BGO detection efficiency, because that relies on GIANT simulations. And of course, that very much depends on also on the available knowledge on, for example, branching ratios of the individual states that are involved. So the 10% there is like what's most significant. And then of course we have like another 2 or 3% depend on for the charge distributions and the stopping power. So these are usually our main factors in the systematics. And then statistics, of course, depends on what kind of resonance we're studying. If it's like you saw the case of the 447 in the isomeric rate for the aluminium, where we only had 10 events. So of course you have a rather large statistical uncertainty, and other resonances again are really strong, and they kind of is negligible compared to the systematics.
Okay, thank you.
Okay, thanks, Nabin. Any more questions for Annika? I'll ask one. So regarding the neutron detectors that you said at the end, can you give some more specific information about, is there a setup already ready to be used, or plans for something like that?
Yeah, so there's plans for something like this. So I wish there was a setup ready to be used. I'll be already proposing experiments this year. No, so we just started experimenting with this because this is in a collaboration with Surrey and Greg Christian as well. St. Mary's, exactly. And so the neutron detectors would be scintillator cubes and then coupled to photomultipliers. And we just got one detector and one photomultiplier shipped to TRIUMF for first tests. And there's funding for a entire array available. So we're just in the middle of the first tests to prove the for a proof of principle for this. And then hopefully within this year, we have all of the basic work performed to then request funding for a total array. And then hopefully this really comes alive in the next couple of years.
Fingers crossed.
Yeah.
Okay, so Luis.
Yeah, hi, Annika. Thanks for the talk.
Hello, Luis.
It's really nice. I didn't quite understand how you overcome the limitation of the angular acceptance for this one experiment.
Okay. So yeah, so you're not per se overcoming it. So you're still, of course, losing all of those recoils that don't make it through the pumping tubes and into your separator. However, what you will learn over the next couple of months or year, that the way we're determining the transmission through the separator is based on these JINA simulations. And by really benchmarking the simulations precisely with like known reactions that have a similarly large cone angle, and still measuring a resonance strength which corresponds to the literature, that you know that you have the benchmark of the simulation under control in your systematics as well. So you're still, of course, you're losing a big portion. However, you know what that portion is, and you know how much is still being transmitted. So it's all a matter of understanding the efficiency under these conditions.
Oh, I see. Thanks.
Okay, thanks. Chiranjeev.
Yeah. Okay. Very nice talk, Annika. I might have a very naive question. You showed one of these isomeric states, I forgot which nuclei, which has the half-life of 7 years or something around that.
Oh no, the ground state has a half-life of 10 to the 5 years, and the isomer has a half-life of around 6 seconds.
Okay. No, because I was wondering if it has a half-life of 7 years, then what would be the statistics in your counter? I mean,
oh yeah. Like, well, again, so maybe there's something misunderstood. So this signature is not what we're like measuring in our detector setup when we're doing a measurement of the radiative capture, but this is just from the decay associated with the beta plus and the electron capture, because you're populating these levels and then they decay into the ground state, and that's how you get your signature in the gamma ray. And this is actually the signature that is measured with satellite missions. So it gives you this observation characteristic. So that tells you, like, this is like in terms of observational astronomy, the signal to see the decay of aluminium-26.
okay.
So that's what you're seeing. But I said it's a short half-life compared to the cosmological scale, not a short half-life, for example, for our measurements, if it were in the lab.
Okay, thank you.
Yeah.
Yes, Phil.
Hi.
Hey.
I won't ask about how to do dragon analysis.
Let's take it offline.
Yeah, it's all right. I'm bugging Matt already. What's the advantage of lanthanum and bromide over BGO? Is it just the energy resolution? Because there's the internal activity as well. So I guess you've got like a pros and cons or something.
So like, yeah, the lanthanum bromides I mentioned at the very end, just in a summary. So that's something that we're trying to do for a more precise measurement of our resonance energy. So the advantage is there, it's even better timing resolution than the BGO detectors. So that gives us a way to relate the signal in our lanthanum bromide detector, the gamma signature, to the signature of the beam. So the RF signal of the beam can then be related directly to the detection in one of the detectors. And that gives us a way to measure the resonance energy even when we're having relatively low statistics. As you saw, this distribution in the BGO detectors as a function of Z that relied on relatively high statistics to determine the center of your distribution with relatively high precision, whereas you don't need that much statistics anymore with the other method. And so that also gives you a way, which is kind of hopefully interesting in the future, when you don't know your resonance energy very precisely. And then if you needed much statistics, then you would lose a lot of time by looking for the resonance, by waiting for the statistics to accumulate. Whereas for the lanthanum bromide method, then within maybe just a couple of runs, you would be able to say, okay, we're on resonance or we're really not. And then you can even make a resonance scan and perform measurements if like there's a large uncertainty on the resonance energy.
That's really cool. I look forward to seeing that.
Yeah, we did first tests actually with like some borrowed lanthanum bromide detectors that we borrowed from the Griffin setup. And the principle of the method works. So now it's just a matter of getting an array to boost efficiency.
Thanks.
Okay, thanks, Phil. Any other questions? Okay, I don't see any other raised hands. So let's thank Annika again for your great talk, very comprehensive. And I have also posted the link for the gathered down room, so we can meet with her in a more chill environment.
A more chill environment. Okay,
Chill
sounds
environment.
good. Okay, yeah.
Okay,
thank
so
you.
again, oh, go ahead. You want to say